Alright, so we're going to do 3 problems, and they're going to build up 1, 2, 3. The first one is going to have only elastic potential energy going on, no gravity, no other work. The second one is going to have elastic energy and some other work going on. And then the third one is going to have elastic energy, some other work going on, and gravity. So we're building up. And this is going to be our strategy for each one of them. For any type of problem in this section, this is what you want to do. So first, as always, identify what target variable you're solving for. Then you're going to pick your points. This is where it starts to differ from previous, right? So we've been talking about like K1 plus U1 plus work other, right, equals K2 plus U2, right? So the points that I'm referring to are the moments, the critical moments that refer to this, like, 1 and 2. So there's some kinetic energy at point 1 and there's some kinetic energy at point 2. And it's up to you to decide when those points are in the scenario that you're analyzing. So a box falling down a ramp, maybe when it's at the top it's point 1 and when it's at the bottom it's point 2. You can choose any points. You just need to choose the points that are useful to you to solve the problem. And you're going to make a simple drawing and identify those points and write down things that pertain to the points, right? Then you're going to write out, I wrote work energy theorem, but really it's not the work energy theorem, it's just the whole energy statement like I had just written out, right? So you're going to write out that whole thing, and you're going to cross out 0 terms. So there's going to be some terms that are going to be automatically 0. So if something is at rest, that means it has no kinetic energy. So you can just cross out K at that point. Or if it's at a potential energy of 0, then it has 0 potential energy, like a rock that's sitting on the ground. Right? It has no potential energy. So you can cross out potential energy for gravity, at least at that point. Or a spring that's at its natural rest state, and it's not stretched or compressed at all. Well, if it's not stretched or compressed, then the elastic potential energy is 0. So cross out 0 terms as you analyze your problem. And then write out the terms in full form and solve symbolically. Full form meaning kinetic energy is equal to 1/2 mv squared. U elastic is equal to 1/2 kx squared, and U grav is equal to mgy. And then work other can be lots of things. It can be just some force, it's just some force through a displacement for everything, but that force can be anything. It could be friction, which is mu sub k times the normal force, or it could be just some tension force that you're exerting that is just equal to some value, or it could be some push force, right? Push. It could be anything that's doing work, right? So that's the full form of our other work. Oftentimes it's friction or some push force. It could be anything though. Okay, so that's our strategy. The last step is to plug in numbers and calculate the answer, and that's the doing the math part, and that is the easiest part, because at that point you've set up your whole problem, you've figured out what you need to do, you've solved symbolically, so you just plug in the numbers and you make sure you're careful when you're punching it into your calculator and spit out the right answer. Okay, so our first problem that we're going to look at here is this one. So we have a glider, and I have a picture of what a glider refers to in a physics problem. This is what they're referring to. This is a glider. So it's just some thing that we're going to consider with some mass, and it's attached to a spring, and it has it's like an air hockey table. So air comes out of these little holes, and so it keeps it frictionless as it slides along the track. It's kind of like a good way of approximating some frictionless system instead of having a block of ice or something. Okay, so a glider with mass m equal to 0.2 kilograms sits on a frictionless horizontal air track connected to a spring with force constant K equal to 5 Newton meters. So you pull on the glider, stretching the spring 0.100 meters, and release it from rest. The glider moves back toward its equilibrium position, x equals 0. So here's the scenario. I'm going to make this smaller, give us some room. Right. Well, first of all, step one, what is the x velocity when x equals this? So we're looking for velocity, and it's when it's come out and then come back in, so we're going to assume that that's probably v2, right, because it's some later velocity after some previous thing has happened. So that'd be like step one. Step two, we want to analyze it and pick our points and see, oops, and see if we can draw a simple drawing. So we kind of have a drawing here, but a simple drawing would be one where we are taking out anything that doesn't need to be there. So we know we have a spring, okay? And x equals 0 is going to be at the natural rest point of the spring. So then we have a glider. I'm just going to call it a box, and we won't consider any friction because it's frictionless. And so what we do is we pull, it says you pull on the glider, stretching the spring 0.100 meters. So that's going to be our 0.1. We have the spring is stretched a little bit. I'm going to do exaggeration, even though it's only 0.1 meters. So this is x equals, and I'm going to do it even further. So we're going to come back just a little bit. Alright, we're out here. This is x equals 0.100. Alright, and this is 0.1. So I'm going to do this, 0.1. And then you let go of it. And so since the spring is stretched, it's going to pull the block back this way, right? And so it comes back this way, and it's asking what is the velocity of the block when the block gets to this position. So something close to 0, but not 0. X equals 0.080. So when the block gets to here, that's our block, and it's moved. It has some velocity in this direction, and we want to know what that velocity is, v2. Its velocity here, you pull it back, and before you let go, it was at rest. So this is v1, and it's equal to 0. And this is x1, and this is x2. Right? So we already have some things, and this has some mass, right? And the spring constant is something. Gave us 5 Newton meters, 5. Right, so we can fill it out more and more if you like, or you can go with what we have here. So we've identified our 0.1, and this is our 0.2. So let's go ahead and go on to step 3, where we write out our energy statement. So the full thing, K1 plus K1 plus U1 plus work other is equal to K2 plus U2. Yeah. So at K1, or at 0.1, what is the kinetic energy? Well, we're holding on to it, getting ready to let it go, but it's at rest. See, V1 is 0. So K1 is 0. So that goes away. But there is some potential energy because the spring is stretched, right? So potential would be equal to 1/2 kx squared. And so x is not 0, and k is not 0 at any point. So there is some potential energy, so we leave that term. How about work other? Is there anything else doing work? We're not pushing it back. We're just letting go. We're ignoring drag force. There's no friction, right? So there's no work other going on here. So that term goes away. And then when it reaches this point, is there kinetic energy? Yes, there is some velocity that it's traveling back to the left. Is there potential energy? Yeah, there's still potential energy because it hasn't gone all the way back to x equals 0 here. So there's still potential energy. So we've crossed out all the terms that we can, and we write u1 is equal to k2 plus u2. So right here it kind of simplifies the scenario. So at the start we have 100% potential energy, and it's in the form of elastic potential energy. And then at point 2, with that snapshot of the scenario, we have some kinetic energy and some potential energy still left to do some work. All right, so what we're solving for is V2, and V2 exists in this term here. So we can say K2 is equal to U1 minus U2, and we can start filling in what these actually are. 1/2 mv2 squared is equal to 1/2 kx squared, because this is elastic potential energy, elastic 1 and elastic 2. Maybe it's smart to write that out just to remind yourself, because there's multiple types of potential energy. Minus 1/2 kx1, 1/2 kx2 squared. All right, and we're solving for V2. So if you move some stuff over, skip some steps like I like to do on the videos, you get that V2 is equal to plus or minus some radical. Sometimes we forget that there's a plus or minus, but it is important. You must choose what makes sense physically between the plus and the minus. K times x1 squared minus x2 squared divided by m. All right, because every term has a 1/2, there's no 2 left in there, just cross that out right away, right? All right, and if you plug everything in, then you get V2 is equal to plus or minus 0.30 meters per second. So we have this plus or minus still. What do we do with that? Well, we take the negative root because the glider is moving in the negative direction. Come back to our drawing. At this point, it's moving this way. Positive x is this way. And so it's moving in the negative direction. So we just think about what physically makes sense for the scenario, because the radical will not decide for us. And so we say we're taking the negative root, and it's equal to negative 0.3 meters per second. There. All right. Yeah, take a moment to think about what that problem might have been like if you didn't have our energy tools to deal with. Thinking back to Newton, you might appreciate more and more what's going on. All right. So now the next problem, I'll put this up. So suppose the glider that we just did is initially at rest at x equals 0 with the spring unstretched. You then push the glider with a constant force F, right? So this is going to be elastic potential energy present and also some other work. We're pushing it. And we're pushing it in the positive x direction. What is the glider's velocity when it is moved to x equals 0.100? So it gives you the magnitude of the force that you're pushing on the glider, right? And we want to know what the glider's velocity is. So this time, our point 1, when the glider is at rest, is at x equals 0, and our point 2 is when the glider is moving in the positive x direction at x equals 0.100. So we're not letting go of the glider, we're just applying some force, right? We're applying some force and it's getting pulled back by the spring. And so like x equals 0 was back here, and we've been applying some force this way. while the glider is working, or the spring force is working against us. Kx is working against us in the other direction. But nevertheless, it's going to be moving in this direction because we're overpowering the spring. And so if we're applying some constant force, it's doing work because it's traveling through a distance, right? This is going to be x equals 0.100. And so what is the resulting velocity, right? So here we have, I'm getting a little ahead of myself because I've already started the drawing, but step one was to, here I'll just do next one. Step one was to identify what we're solving for. We're solving for V2 again, right? V2 equals something. Step two is to do a drawing, and that's what we've started on. So this is x1, this is x2. V1 starts at rest, so it's 0. V2 is what we're solving for. There's some spring constant k, and it's going to be the same as the last one, so I think that was 5. And I think it gives us the force. We might as well write that in there, 0.610 newtons. All right. So we have everything that we need. Step 3 is to write out our energy statements. So we're on step 3. We write out everything. K1 plus U1 plus work other is equal to K2 plus U2. Alright, so thinking about, and identifying our points. I said it verbally, but here, when the box is at x equals 0, that's point 1. And here, where the box is at x equals 0.100, that's point 2. Alright? So at point 1, x is equal to 0, and so if this is the elastic potential energy, right? That's the only thing present, there's no gravitational potential present, then that's going to be 0. Is there kinetic energy? No, because it starts at rest, so there's no kinetic energy either. And is there some work being done? There is, because we are applying a force. Immediately at the start, we're applying some force. Okay, and then we have K2. At this point, yes, we have kinetic energy because it's moving, and yes, we have potential energy because the spring is stretched. So what this works out to be is work other is equal to K2 plus U2. All right. In other words, if we were not to apply a force, adding mechanical energy to the system, then there would be no mechanical energy because everything's at rest and it has no potential energy. The spring is not stretched. It's starting at that x equals 0 point, right, and not moving. So we must apply this external force to add mechanical energy to the system, to stretch the spring to the right and give it some velocity. Okay, so work other is just a standard push force through a distance. So that's F. So work other is equal to F times delta x, right? The displacement of the block. And U is equal to the elastic potential energy. So U equals U elastic, which is 1/2 kx squared, right? So if we plug that in, we get that F delta x is equal to 1/2 mv2 squared plus 1/2 kx2 squared, right? We've just filled in what these specifically are. We've written out the full version. I think that was step 4 in my steps above. And then what we're wanting to solve for is V2. So that's right here. And so if we solve for that, we get, and this delta x, right, is just x2 minus x1. Don't get thrown off because of that delta. And x1 is equal to 0. So delta x is just 0.100 minus 0. That's what you would plug in for delta x. So if you solve for b2, you get this plus or minus again because it's a radical, and we'll have to think about which root we want to take. 2 f delta x, which really equates to, like I said over there, really equates to x2. Now I'll write delta x because it makes more sense to leave it like that. Minus k x2 squared over m. All right. And if you plug it all in, then you get v2 is equal to 0.60 meters per second. Is the positive or negative root? Well, the velocity, we're going in the positive x direction, so it's the positive root. So we have to consider it, but it makes sense in this case. It is the positive root. Boom. There it is. So we even had some push force going on, but we could handle it just fine. All right, and then finally the last example. This is a much more complicated problem, but we can do it just fine. So we have a 2,000 kilogram elevator, and it gives you the conversion to how many newtons that is, because we're on Earth, and so it's just doing m times g, right? With broken cables in a test rig is falling at 4 meters per second when it contacts a cushioning spring at the bottom of the shaft. The spring is intended to bring the elevator, to stop the elevator compressing 2 meters as it does so. So, oops. This is the one. All right. So, I'm going to put this up here so we can see the top half of this page. So I'm not going to reproduce this drawing, but we can see the drawing that it gives us here. All right. That way we see, without me having to waste 5 minutes drawing all that out, this is what's going on. So here's the elevator as it's falling. And point 1 is when the elevator is at this point where it's just made contact with the spring, right? So it's been falling, and right when it makes contact with the spring, that's going to be our point 1. It has some velocity, and it has gravity acting on it, and it has some pull from the cable acting on it, and it has some spring force that's going to begin acting on it. Point 2, it's compressed the spring a certain amount, and it's come to a complete stop. So it's gone through this displacement, and its velocity is 0, and it has some potential, elastic potential. Yeah. And since we have to define x equals 0 at the compressed, or the uncompressed point of the spring, the natural resting point of the spring, then it's still going to have some gravitational potential at the point 1 and point 2. All right, so we're going to apply our same steps. So first, what are we trying to solve for? What is the necessary force constant K for the spring to make all of this happen? That's what we're trying to solve for. Yeah. Okay. So, new color, that's a nice one. So, force constant K of the spring, right? That's not K sub S, it's not friction force, or mu sub K or anything like that. It's the friction force, it's just K. Now we're going to pick our points. We already kind of talked about that on the drawing. And then we're going to write out the work energy theorem. So I'm going to skip 2 because we just talked about 2. 3, we're going to write out our full energy statement. And this time we have everything. We have, well, here, I'll simplify, I'll do the drawing for this. So here, we have the ground. Alright, so point 1 is going to be over here, maybe point 1, and this is going to be point 2, just like they did. Alright, so point 1 is going to be when the spring is not compressed, so right here, that's going to be x, or we'll call that y because we're talking about in terms of height, and it's vertical. So y is equal to 0 there. And we have this box attached to it, which is the elevator, some mass, right? We have some force acting on it, which is from the cable, and that's equal to, they tell us, 17,000 newtons. The mass is 2,000 kilograms, so I'll stuff that in there. M equals 2,000 kilograms. Alright. V1 is the speed that it's going as it's falling. V1, because this is point 1, V1, right, is equal to 4 meters per second. Right. And we have gravity acting on it as well, so we have weight equal to mg. Alright. And it's 2,000 kilograms, so it tells you it would be 19,600. So I'll do 19,600 newtons. Alright, so that's our point 1. Now let's come back over, talk about point 2. So point 2, the spring is compressed. So I'll just do this a lot more compacted. Alright, and it's lower than the other one. And so at this point, spring is compressed, and we say y is going to be equal to something less. Because if this is 0, and gravity works down, and y increases in the upwards direction, then we have to say y is equal to something negative here. And it's negative 2 meters, because that's where we want the spring to stop, 2 meters. Alright. We have our block, same mass, and we have gravity working on it, but V2 is equal to 0. So we have mg working on it, but there's no there's no kinetic energy. Alright, so that's our quick drawing. Let's write out what's happening at each step. Alright, so step 3, I'm going to write all of our stuff out. K1 plus, we'd usually write U1, but we know that there's both elastic and gravitational potential, so I'm going to write each of them out separately. U elastic 1 plus U gravitational 1 plus work other is equal to K2 plus U elastic 2 plus U grav 2. Right? So we have everything involved here. Everything. Alright. So, how do we go about solving it? Well, the next step would be to cross out 0 terms, yeah? So at the start, what we have is some kinetic energy, because it's falling. Do we have elastic potential energy? Well, the spring is not compressed at all because it's at its natural rest point. Because point 2 we've chosen right when it first makes contact with the spring, but not as it started compressing it. So we have no elastic potential energy. U grav, that's mgy, right? mgy1 in that case. Well, y equals 0 is where point 1 is. And so there's no gravitational potential energy there either, because we've defined the ground to be where the spring is uncompressed. It kind of seems weird because we also have a ground drawn there. But because we had a spring, we had to put y equals 0 at the point where the spring is not compressed at all. Work other. We do have some other work because we have the cable that's pulling up on the elevator that's doing constant work on it. And over here, the elevators come to a stop, no kinetic energy. But we do have some elastic and gravitational potential energy on the right because the spring is compressed, so it's pushing back up on the elevator. And mgy2, y is not equal to 0 there. Neither, of course, is mass or gravity. So we do have elastic potential, gravitational potential energy in our point 2 scenario. So if we rewrite this without our 0 terms, K1 plus work other is equal to U elastic 2 plus U grav 2. All right. Next step is to fill in actually what these are. 1/2 mv1 squared plus work other, and we can fill in, I guess, what that is because we know that it's going to be some force through some delta y, and we labeled the force with this cursive F, so we'll do this. There we go. And because it's kind of a friction force is why it's a cursive S, because even though it's a cable and it is tension on the elevator, it's this constant tension as it goes down, so it's kind of the same operationally as a friction force. That's why we've done it. And then elastic potential energy is 1/2 K, and it's Y in this case. Yeah, Y2 squared. Right, and y-axis are interchangeable. It's just we're working in the vertical for this problem, so we use y. Plus mgy2. All right, there it is. What are we solving for? What are we solving for? And remember, delta y here is y2 minus y1, and y1 happens to be 0, and so it's really just y2. When you go to plug your numbers in, and you're checking and doing all of this on your own, on your paper, with your calculator, just to make sure you can do it. So what are we solving for? We're solving for K, the spring constant that must be needed to make all this happen. So we only have one K in the equation, so that makes it kind of easy. We just need to solve for it. So go ahead and make sure you can do this by doing it yourself on each of these. It's very different watching your instructor go through it versus going through it on your own. Everything seems very easy, and you say, oh yes, I can definitely do that. I know exactly what he did when you're watching me go through this. But then when you try to do it on your own, it's a little bit different sometimes. Alright, y2 squared. I'm obviously skipping a bunch of steps just for the sake of time and to encourage you to do it on your own. But f delta y minus mgy2. Alright, and if you plug everything in, you should get the K, the spring constant needed to make this scenario happen, is 10,600 newtons per meter. Which is quite a lot, but 2,000 kilogram elevator is quite heavy, and it's going down at 4 meters per second, which is kind of fast. Alright, so that was a problem that had every category of thing, so it should give you a good template for doing all types of problems in this section. You might have multiple other forces doing work on the body, in which you would have to find the total force vector that does the work on the body, right? So we just had that cable force, but you might have some push force acting on something, doing work that contributes to work other. You might have some friction force that's contributing to it. You might have some tension force, that's contributing to it. You might have a lot of different things, and you just have to find the total force vector, like we did a few chapters ago. Total force vector and the component of that total force vector in the direction of motion to find work other, because then you'd have the total force and multiply it by the total displacement, right? So these problems can really build up, but you really have the basic building blocks to figure them all out. Okay, so we'll wrap up this lecture in the next video, and we'll talk about non-conservative forces and conservative forces, and the law of conservation of energy, which is a really cool summation kind of concept that is really important throughout all of physics. All right, see you next video.